welcome to the video lecture for section 4.3. This is for STA 2023. My name is Jorge Gavillan. So we're going to be talking about complements, conditional probability, and Bayes' theorem in this section. So we're going to extend the use of the multiplication rule to include the probability that among several trials we'll get at least one of some specified event. So we consider this to be the conditional probability. Now the probability of an event occurring when we have additional information that some other event has already occurred. We provide a brief introduction to Bayes' theorem. So when finding the probability of some event occurring at least once, we should understand the following. At least one has the same meaning as one or more. Now the complement of getting at least one particular event is that you get no occurrences of that event. So the probability of getting at least one of some event, so let A be equal to getting at least one of some event, and then the complement of A getting none of the event being considered. Sorry about that. And so the probability of the complement of A, the probability of the event A does not occur. So we're going to subtract the result from 1, that is evaluate the expression. The probability of at least one occurrence of event A is equal to 1 minus the probability of no occurrence of event A. And so here's an example. A study by Square Trade found that 6% of damaged iPads were damaged by bags or backpacks. If 20 damaged iPads were randomly selected, find the probability of getting at least one that was damaged in the bag or backpack. Is the probability high enough so that we can reasonably be sure of getting at least one iPad damaged in a bag or backpack? So step 1, let A be at least one of the 20 damaged iPads was damaged in a bag or backpack. Identify the event that is the complement of A. So the complement of A, not getting at least one iPad damaged in a bag or backpack among the 20, is equal to all 20 iPads damaged in a way other than in a bag or backpack. Step 3, we're going to find the probability of the complement by evaluating the probability of the complement of A. So the probability of complement of A is equal to the probability of all 20 iPads damaged in a way other than in a bag or backpack. And so that's going to be 0.94 times 0.94 because the probability that it is damaged is 0.06, so the complement of that will be 0.94. Then we're going to find the probability of A by evaluating 1 minus the probability of not getting A, which in this case will give us 0.71. So how do we interpret this? For a group of 20 damaged iPads, there's about a 71% chance of getting at least one iPad damaged in a bag or backpack. So this probability is not very high, so that to be reasonably sure of getting at least one iPad damaged in a backpack, more than 20 damaged iPads should be used. The next thing is conditional probability. So the conditional probability of an event is a probability obtained with the additional information that some other event has already occurred. So the probability of the probability of B given A denotes the conditional probability of event B occurring given that an event A has already occurred. So the conditional probability of B occurring given that A has occurred can be found by assuming that event A has occurred and then calculating the probability that event B will occur. So the probability of B given A can be found by dividing the probability of events A and B, both occurring, by the probability of the event A. And so usually the best thing to do is use a contingency table. So if one of the 555 test subjects is randomly selected, find the probability that the subject has a positive test result given that the subject actually uses drugs. That is, find the probability of a positive test given that the subject uses drugs. And so B, if one of the 555 test subjects is randomly selected, find the probability that the subject actually uses drugs, given that he or she had a positive test result. That is, find the probability the subject uses drugs, given that they got a positive test result. So the first approach is we want the probability of positive test given the subject uses drugs. So if we assume that the selected subject actually uses drugs, we're dealing only with the 50 subjects in the first row of the table. Among those 50 subjects, 45 had a positive test result, so we get this result. So the probability of a positive test result, given that the subject uses drugs, is 0.9. And remember that I mentioned earlier in class that when we do conditional probability, our sample space changes. And in the formal approach would be the same result can be found by using the formula for the probability of B given A, given with the formal approach that the probability of B given A is equal to the probability of positive result given that the subject uses drugs, where B is the positive test result and A is the subject uses drugs. So using this information, we get that the probability of subject uses drugs and had a positive test result is 45 over 555. The probability the subject uses drugs is 50 over 555. And you can see here that we get the following. If we divide this fraction, we end up with 0.9. And in reality, using the contingency table, we can actually find these values without having to go. He showed two different ways of doing it, but in reality, we really just do it one way using the table. So by comparing the intuitive approach to the formal approach, it should be clear that the intuitive approach is much easier to use and is also less likely to result in errors. So here we want, for B, we want the probability of subject uses drugs given that they got a positive test result. There's the probability that the selected subject uses drugs given that the subject had a positive test result. So if we assume that the subject had a positive test result, we're dealing with the 70 subjects in the first column of the table. So among those 70 subjects, 45 use drugs. So the probability the subject uses drugs given that there's a positive test result is 45 over 70, which is about 65%, 64%. So the first result, the positive test result given the subject uses drugs is a 90.9, indicates the subject who uses drugs has a 0.9 probability of getting a positive test result. The second result, probability the subject uses drugs given the positive test result is about 0.64, indicates that for a subject who gets a positive test result, there's about a 64% chance that this subject actually uses drugs. Now note that the probability of positive test result given the subject uses drugs is not the same as the probability that the subject uses drugs given that they got a positive test result. So in the prior example, the probability of positive test result given the subject uses drugs is not equal to the probability of subject uses drugs given the positive test result. This example proves that in general the probability of B given A does not equal the probability of A given B. Now there could be individual cases where these are equal, but they're generally not equal. So to incorrectly think that the probability of B given A and the probability of A given B are equal, or to incorrectly use one value in place of the other, is called confusion of the inverse. So confusion and inverse. Consider these two events. D is dark outside, M is midnight. So in the following, we conveniently ignore the Alaskan winter and other such anomalies. So the probability of D given M is equal 1. It is certain to be dark given that it is midnight. Probability of N given D is 0. The probability that it is exactly midnight given that it is dark is almost 0. So here, of course, these two are not equal to each other. So the confusion of the inverse occurs when we incorrectly switch these probability values. We'll think that they're the same. And that's the end of section 4.3. Thank you.